Okay, let's unpack this. You shared a great stack of sources with us, all focused on the fundamental building blocks of Python.
Yep.
And today we're going right to the heart of what makes Python so efficient and, so powerful.
That's right. Today we are talking about the
The
dictionary.
dictionary.
If Python had a hidden superpower, I think this would be it. It's mapping type. We're going to dive deep into dictionaries, how they're built, why they're so fast.
And crucially, how to manage them so you can avoid some pretty serious coding headaches down the line.
Exactly.
So our mission today is to cut through the basics and really give you the absolute essence of what you need to know.
Right. We'll cover what they are, how to make them, but also the really critical stuff like mutability.
In the real-world applications, we want to show you exactly why they are so valuable.
We want you to walk away understanding that speed, that, near instant lookup and the specific nuances, especially around copying.
That's where people get tripped up.
That's where even experienced programmers often trip up, yeah.
We all start with lists and tuples. They're simple. They're sequential containers.
Mm-hmm.
But a dictionary, it immediately moves us into a much more advanced league. It's not about finding an item by its position.
No, it's about finding it by its name.
Exactly.
Precisely. If lists and tuples are, say, organized boxes that you have to check one by one.
A dictionary is more like a massive pre-indexed library.
That's a great way to put it. Fundamentally, it is another compound type, a container, but it stores data as a lookup table.
And this is Python's official mapping type, right?
It is. It's similar to things you'd see in other languages like associative arrays in C++ or the map container in JavaScript.
Okay, a lookup table implies a relationship. What exactly are we mapping here?
We map a key to a value.
A key to a value.
Think of the key as the unique identifier, the label. And the value is the data that's associated with that label.
And there are rules here. I know the rules are pretty strict for the keys, but flexible for the values.
Completely. The key must be of an immutable type. This is absolutely vital.
So we're talking strings, numbers.
Strings, numbers, or tuples. The key reason for this, and this ties directly into the dictionary speed, which we'll get into, is that keys need to generate a consistent, unchanging hash value.
A hash value.
Right. If your key could change, Python wouldn't know where to look for your data. It needs that static identifier to index against.
So the key is the address label, and you can never, ever change that label. But a package itself, the value, that can be anything.
Anything at all. The values can be heterogeneous. You can map a string key to a number, a tuple key to a list, or even map a key to another dictionary.
That flexibility is what makes them so useful for modeling complex, real-world data.
It is.
And speaking of versatility, there is a crucial modern detail here, something that makes dictionaries today fundamentally different from how they used to be.
Oh, absolutely. This is a huge aha moment for anyone who learned Python, say, 5 or 6 years ago.
What changed?
It's the order. Up until Python 3.6, the order you inserted elements into a dictionary was, well, basically arbitrary. You couldn't rely on it.
Right, you'd print it out and it would be all over the place.
Totally random. But that changed. Starting with Python 3.7, and as an implementation detail in 3.6, dictionaries now remember and preserve the order of the elements inserted.
That is a massive operational shift.
It's huge. I mean, I remember dealing with old Python 2 code where you have to pull in the orderDict class just to keep things sequential.
That whole extra step.
And now that complexity is just gone. Standard dictionaries guarantee insertion order is preserved. It simplifies so much.
So no more worrying about your frequency counts being printed in some chaotic random order.
Exactly.
That is incredibly helpful. But let's get into the dictionary's real core power.
Speed. The speed.
When you search for an item in a list, worst case scenario, you're looking through every single item.
That's linear time. O of n, as they say.
But with the dictionary, we are talking about near constant time.
Yeah.
O of 1. How does it do that?
It all comes down to the hash table structure that dictionaries are built on.
The hash table.
So when you define an immutable key, Python immediately runs it through a complex hash algorithm. This algorithm computes a small integer, like a unique fingerprint or a checksum for that key.
So it's basically an instant address.
Exactly. Think of Python's memory as a huge apartment building. A list search is like walking floor by floor, knocking on every single door.
Tedious.
Very. But with a dictionary, the hashing algorithm instantly tells Python, this key lives in apartment 42B. It just goes straight there. It avoids the search entirely.
That's a powerful analogy. It means that whether you have 10 items in your dictionary or 10 million,
The time it takes is roughly the same.
finding the value for a specific key takes about the same amount of time. That's the difference between a millisecond and, potentially waiting seconds.
The speed advantage is tremendous, and this is why when we access values, we use the key inside those square brackets. You're not asking Python to search, you're just giving it the address.
Okay, so if we're manipulating data, we often need to check if a key already exists.
Yeah.
What happens if I ask for apartment 42B and it doesn't exist?
You get a key error.
And your program crashes?
Your program crashes. And that brings us to two essential operators, in and not in. They let you check for a key's existence without risking that error.
So it's foundational for writing robust, crash-proof code.
Absolutely. Instead of just trying to access it and hoping for the best.
You could just ask, hey, is the key in my dictionary?
Ugh.
And then safely go ahead if the answer is yes.
Correct. This is so useful for data aggregation, like the frequency counting problems we'll talk about. You need to know whether to create a new entry or just increment an existing one.
Okay, so we have the speed and the structure, but that introduces a complexity, and it's something we touched on earlier. The mutable nature of the dictionary object itself.
It really does. We have to remember that while the keys are immutable, the dictionary container is not. You can add things, delete things, update values all you want.
And that has some pretty big consequences for how they behave, especially with functions.
Huge consequences.
If I pass a list into a function, and the function changes that list, my original list outside the function is also changed. Is the same true for dictionaries?
Absolutely. Because the dictionary is a mutable type, when you pass it to a function, Python passes it by reference.
So the function gets a pointer, basically, an address to the original object.
That's it. So any change made inside that function, adding a key, changing a value, it affects the original dictionary. Globally.
Which can lead to some really unexpected behavior if you're not careful.
Or sometimes that's exactly what you want, but you have to be aware of it.
And this leads us to where people run into those silent, maddening bugs. Copying.
Oh, yeah. If you don't understand the difference between an alias, a shallow copy, and a deep copy, you are asking for trouble.
So let's go through the horror stories, starting with the most common mistake, the alias.
The alias isn't even a copy. If you use simple assignment, like dict A, dict B.
You're just making two names that point to the exact same object in memory.
Exactly. You change a value using dict A, and it immediately shows up in dict B. They are the same thing. You never, ever assume assignment creates independent data.
Okay, so the first real attempt at independence is the dot copy method, the shallow copy.
Right, the shallow copy. When you do new dict, original dict copy, Python creates a brand new dictionary container, which is a good start. The problem is what happens if your values are also mutable, like lists or other dictionaries.
So the shallow copy makes a new top-level container, but the references to those inner things, those are still shared.
Precisely. The shallow copy only copies the references to those nested objects. So if you have a dictionary mapping names to, say, a list of scores, and you change a score in the list inside your shallow copy, the original dictionary sees that change too.
Oh, that's nasty.
I once spent an entire afternoon debugging a financial model because a nested list of quarterly results wasn't deep copied. The numbers kept changing in two different reports at the same time. It was a total nightmare.
The perfect cautionary tale. Right. And that nightmare is exactly why we need the safeguard. The deep copy.
Yes, the deep copy. You have to import the copy module and use copy.deepcopy. This is the heavy-duty option.
So what does it do differently?
It creates a completely independent copy of the dictionary, and it recursively copies all the mutable objects inside it, no matter how deep they're nested.
So the main takeaway is a shallow copy only protects that top layer.
Right.
For anything complex with nested lists or other dictionaries, you have to use deep copy to guarantee they are truly independent.
Absolutely. For anyone listening, this isn't just theory. This is vital knowledge that prevents that silent, insidious data corruption.
That is a massive step towards writing more robust code. Okay, let's switch gears from the technical nuances to where the dictionary really shines. Real-world problem solving.
Application time.
What do we use these powerful lookup tables for?
Well, the most fundamental and powerful use case is frequency counting. Tallying data. Dictionaries are just unparalleled for this.
Why is that?
Because you can instantly check if you've seen an item before, and if you have, you can instantly increment its count. No searching required.
We had two great exercises in the source material that show this off. The first one was pretty simple, counting letter frequency in a word.
Right, and that exercise is really designed to highlight the .get method.
Ah.
Instead of that if key in dictionary check, you can use dictionary.get. Key, default value. If the letter's found, you get its current count. If it's not found.
You get the default value, which you'd set to 0.
Exactly. Then you just add 1. It simplifies the logic a lot.
And the second exercise was a bit more like a real-world data cleanup problem.
Yes. It challenges you to read some text, ignore the case, get rid of punctuation, and then print a clean frequency table of letters, all in alphabetical order.
So if your input is like this is string with upper and lowercase letters,
The dictionary processes it all down. It turns T and T into the same key, and then it just tallies up the occurrences.
that is a practical skill that translates immediately to so many things. Managing inventory, tracking web traffic, counting unique user actions.
It's all about aggregation. And if we connect this to the bigger picture, dictionaries are really the backbone of managing complexity in programming.
How so?
They're key to solving so many advanced problems because they allow for that instantaneous, key-based lookup instead of a slow, painful search.
Okay, let's pull out a couple of those competitive programming problems from the sources to really make this concrete.
Good idea.
How does the dictionary structure solve the core puzzle in these? Let's start with Babelfish.
Babelfish. It's basically a language translation problem. In the real world, this is how all lookups work, from glossary apps to API mapping.
The core puzzle there is speed, right? You have a huge dictionary of translations and you need to look up words instantly.
Exactly. So you map the source word, an immutable string as the key, and the translated word as the value.
And thanks to that hash table we talked about.
Translating 10,000 words takes almost the same time as translating one. The dictionary provides that near instantaneous lookup. It turns a slow search into a series of super fast lookups.
Fantastic. Okay, what about something more complex, like the ACM contest scoring problem? That involves tracking multiple variables for a single thing.
That's a classic example of mapping an immutable identifier to a mutable set of data.
Ah, okay.
The problem ID, say problem A, is our key. But the value isn't just one number. It's a list or tuple of data.
Like penalty time, number of wrong attempts.
And whether it's been solved or not, all bundled together.
So the dictionary lets you instantly find the record for problem A and update those 3 pieces of data all at once.
Exactly. You're mapping a unique static identifier to a flexible data structure that you can update in real time. This is why dictionaries are everywhere, from managing user sessions on websites to tallying votes.
So to quickly summarize our deep dive here, dictionaries are Python's fast, flexible lookup tables. They're essential for mapping immutable keys to all sorts of flexible values.
And the secret to their speed is that complex hash algorithm that gives us that O of 1 retrieval.
And critically, understanding their mutability. The fact that passing a dictionary to a function passes it by reference.
And you absolutely must match the difference between an alias, a shallow copy, and a deep copy to keep your data safe.
So, since dictionaries are the backbone of efficient translation, complex scorekeeping, and counting things, we want to leave you with a provocative thought. If you look at your own complex real-world data, tracking your fitness goals, managing an inventory, planning a big project, how could you use this structure? How could mapping unique, immutable identifiers to flexible data sets give you better clarity and faster processing?
That structure is so often the hidden solution to data chaos. Go forth and map your world.
We'll catch you on the next deep dive.